Now we've got a bit of a compiler or a parser for Pascal-like Y that the grammar works, and we've used the debug mode to show that it works on the test program. The next thing to do in building a compiler is to get the parser to build a tree. We can see in the original calculator that we also built a tree. So if we look at the arith.y file that we made in the calculator, it called a create node. So each time it recognized a rule, it added a node to a tree, which ultimately ended in a parse tree. And it includes some definitions of a tree, and here's the node of the tree, and here is a method or a function called create node that was used to add a piece of the tree every time the rule matched. In the coursework, we've been given a skeleton file which we can pick up in the set of files containing the test programs. It can be downloaded, or you can get it from the T drive. And you can see in the compiler skeleton we've been given a slightly different structure of a tree that has 3 items, or a ternary tree rather than a binary tree, and also a symbol table has been defined for us and some other things. So what we need to do is start merging this skeleton code with the parser that we've got to build that tree. So the easiest way to go about that is to take part of this skeleton at the beginning, some standard headers and some standard libraries and the parse tree definition and the symbol table definition and all of these things, except down to the sort of token lines, but we've already got those. And we can go to our grammar file, Pascal-like .y, and we could paste that in the top. And it's got some examples of token definitions which we can leave for the moment. Then it has the grammar rules, and then at the bottom it has some other code which we can copy and paste to the bottom of the file before the include. So we can save that file, and now we've merged in it the top and bottom of the skeleton file, but we've left our grammar rules the same. The reason why we're doing this is to prove it hasn't broken it. So if we Bison this file with the extra definitions built in, and then we call GCC, we can see it still compiles, and we can run it through our test program. Get the right file. We can see that the test program doesn't do any errors, so we haven't broken it. We can do the same with the other skeleton file. .l skeleton, which has some code that we can put in the Lexa file. And basically it's this little part to declare a symbol table which goes inside the curly parentheses which we already have. So if we go to Pascal-like.l, we put that in there. Don't need that extra thing. We can declare the symbol table, which we'll need later in the top part. and we can just prove to ourselves that it doesn't break things by calling the flex and the Bison and the GCC and we could run it on the test program and everything still works. So we've included all these decorations from the skeleton in a grammar file and an Alexa file. So if we get any faults shortly, they won't be in that code. So what we need to do now is add some code to each of these rules that look a bit like those in the other one. I'm going to split the window so we can look at both things at once. So if we look at the arith.y file, we will see that under the main part of the program we created a tree, a variable to store the tree, and then the tree, and then in all the others we said $$ equals create node, which I'll explain as I go along. So we've got examples of doing that in the skeleton. So here's an example of the rule. So we can declare a ternary tree in which to store the main program and paste it in there, and then we could perhaps assign to that the parse tree that we create, and that will create as the parse tree for this program. Now let me explain what these $ things mean. So $1 relates to this begin terminal symbol, $2 relates to this statements, and $3 we just count from the colon. So the only thing here that has any tree in it is actually $2, and $3 doesn't. So we need to fill in exactly 5 arguments for this, and that's what the null name is for. So here we can create a node for a program storing nothing and linking it to the tree for statements. That's what that says. Now we can do something similar for the statements rule, and our little skeleton says for the rule underneath, which in this case is the block, which it would be in the coursework, but we're not doing the coursework here, we're doing a different example. A rule where statements is a statement, so we can paste in something that continues to build the tree. So we don't say block because it isn't a rule for block. We need to show that this comes from the rule statements, so we type that node for statements. Then we've got to put in the pieces here, and it's just got a $1 because that's all there is, and then we can put null, comma null. And that does that one. For the following rule that says statements semicolon statements, we could continue with that. It is for the rule statements, but now as well as a $1 we've actually got another tree in $3. $2 is just a terminal symbol, the semicolon, and we don't need to store that information. So that shows how we can build the tree. What we now need to do is go on for the other rules and create something similarly. The other thing we also need to do is at the top here in the code there's a enumerated type where we declare these names used to type the nodes. So we had program and we had statements. That's what we've got so far. Now we can actually automate this, and I'll show you how we could automate it using keyboard macros. So I've done the first two. We need to follow that same pattern for the rules. So what we need to do is, the first thing I'm going to do is actually split the window and go for the enumerated type here and actually position it at the right position, and then I can actually put the names of the things in. So I need to create some kind of macro, and Control X open parenthesis starts to define a keyboard macro. So then I want to look for a regular expression, say for the beginning of a rule. So I do a regular expression search for the beginning of the line, and then A to Z, a name of a thing which may contain an underline in it, and that's probably all I need, and there's more than one of those letters, followed by a space and followed by a colon. So now we've found all of the things at the beginning of rules. So if I go back to set a mark, go to the beginning of line, copy that, I've actually got the name of a rule. I can now go up to the other thing, add a comma, a space, paste that in, go back a word, uppercase it, go back in here. Then if I go to the end of that line, I can probably now indent a bit, insert $$ equals create node, nothing, I'm not using that at the moment, and then I can paste in that name, go back to the beginning, uppercase it, put a comma, and for the time being I could go null, 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 close bracket, semicolon, and then I can close off that, and I've managed to create that first node for that statement and add its declaration. So I can do Control X, close bracket, and I've defined a keyboard macro, and I can do Control X E and execute it, and it's done the same for if statement, and I can execute it, and it's done it for while statement, I can execute it, and it's done it for assignment statement, and I can execute it, and it's done it for condition, and I can execute it again, and it's done it for a relative operator, and I can execute it again, and I can execute it again, and I can execute it again. If I execute it again, it goes ding, meaning it's done them all. Now you can see there's a few errors in that because I didn't uppercase all the words, but that's okay. I can now tidy that up. So I can just manually patch up the bits I didn't do and make sure it looks nice and tidy, but I saved myself a bit of time. So now what I can do is just indent this a little bit. And now I can copy that and manually put it in there, and there, and there. And I can also change one of the nulls to $1, $1, and $1. So that one's done. Then I can take the next one. I can fix the uppercase. I can fix the indentation. And then I can fix this part. So I need to remember here the condition, which is $2. That's a tree. And I can remember the statement, which is $4. This one, the next one, I can indent it. And fix the uppercase part. And here I have to again remember a condition, which is $2. And a statement, which is $4. Go to the assignment statement. I can indent it a little bit. Uppercase it, and I can remember the tree that's $3. Now on this particular one I've got an identifier on the left which I'd like to know. The identifier is not a tree, it's a token, and that one goes there, $1. That's what the first parameter is for. I'll explain a little later when I've got all the others how we can get that value. That's how we pick up the lexeme value. So here we've got expression, rel-op expression, so we actually got 3 things we need to remember. So now here we've got $1, $2, and $3, which is actually one of the reasons why we've got a ternary tree, because sometimes we've got 3 things to remember. So here there's actually nothing to remember. And we can copy and paste the same thing. But now we've got 2 tree nodes and we wouldn't be able to tell the difference between the 2 nodes. But actually we can cheat and we can store the name less than in that node in the first parameter. Can store greater than in that node, and it enables us to pick out the difference between them later on when we come to code generation. So here we've got an expression and we've got 3 things to remember again. $1, $2, and $3. However, this time when we paste that in, we only need to remember $1 goes null again. Now I've got another operator one like before. We can actually remember that this is a plus by using the plus token there. Remember that this is a minus, by remembering the minus up there, and this last one we can tidy up. Now here we're getting a number, which is a token, and we want to pull up its lexeme value there. And the same for that one. Now here's the problem, how can we tell the difference between a number and identifier here? We need some way of doing that. So we might actually have to do something different in the tree and actually call that number value and that ID value, which means we need to go in the top of the tree, the file, and actually add number value and ID value to the list of enumerated types, and as it says, we add more types every time we add a tree node. So we've now built all the tree nodes. It wasn't totally automatic, but we used mechanical means to create a bit more of them. So I said I'd come to explain later why sometimes we pulled out the value of tokens and got their lexical value. This is when we need to go back to the lexical analyzer and we see we've added a bit of initial code to do stuff. We need to do something for these two token types, ID and number, and actually return some information that helps us. So there's two ways of doing that. We could create a new macro for things that return values that just deal with the value, or edit this one. So I could call it ID token, and I could call another one number token, and I have to change those macros to make that work. So what that means is I have to clone this token macro a couple of times, and I could call number token, and I could call it ID token, and I've also got to clone the other one a couple of times. So whether or not print is turned on, I will have a macro. So now if it's a number token, I can actually say number and I could print the value of the number. For the ID token, I could print the value of ID as a string from text, the built-in variable we've already looked at that contains that. If we were to return these, what we have to do is add some extra code in here, and it gets added to YYL val, and it's a variable called ival, the integer value of that, and a to I of YY text. Gets stored in there. Yeah, if if it's an ID token, we have to do something different, which is put it in the symbol table. So to see how we put it in the symbol table, I'll split the window and actually we can look at the .l skeleton, which explains how to do that for an identifier. It says you have to do this y_l_val install ID. So I can just copy that piece of code out of there and paste it into there. And magically now we're doing the right thing for a symbol. So now if it's a number or an ID, we can save its value. We can pick it up in the parse tree when we build a node, and we can create all the nodes. So let's go and build this all and see how it works. So I've changed all the files, so I have to run them through Flex. I have to run them through Bison. Now we've got a lot of type errors here, and all these nodes have no declared type in the .y file. So that's a part that I've skipped over. So if I go to the other skeleton file, you can see it's typed these tokens, and that's what it's asking that we do. So for the tokens of ID and number, we say they return an I-val, because we've assigned to the I-val. For the tokens that don't return an I-val, we say nothing, but we also have to, as it says here, rules return a tree type. So we have to type them. So for each rule, we now have to add them in there. So if I'd actually knew I had to do that, I could have added their name there when I wrote my macro. So basically for all the things in this enumerated type, we can go to the enumerated type here. I can just steal all these, and I want them lowercase again. Put them in this other thing. Just saves a bit of time. So I can lowercase all of these things because they're the name of the rules. So the rule's called value. So there we are. I can save that. And then if I go into Bison, it's a lot happier. Oh, it's complaining about some extra commas. I'll just take these out. So, looks like I might have an error in the create nodes. Well, that's not too difficult to fix. I search for the expression rule. So, here we are. It says number 2 of expression has no value. It's binary op at actually has a capital O in the middle, which I didn't pick up, so I can fix that. Oh, is there a stray comma? Yes, there is one. Right, so now I've got all the create nodes in, flex builds, Bison builds, so I can just run it through GCC and check that it all compiles. There might be some typos. So it's got undefined reference to install ID. I wonder if that's because I haven't defined it. Let's have a look. Let's go to Pascal like.l, go to the bottom of the file. Oh no, I forgot to put that in. If we go to the SPL01 skeleton, there's the definition of some methods right at the bottom, which have to be pasted in. And I forgot to do that. So we just go to flex. We go to Bison. We go to GCC, and the whole thing builds, and I can run that parser on the test program, and it works, and it's built a tree. I mean, the next question is, how do I know it's built a tree? We might not. So what we have to do now is, it's one of the answers to one of the standard questions, is how do I print a tree? It's question 10, and I've given a little print tree routine here, which you can just copy out of the questions. And now I can go into my .y file and just add that, as it says put in other auxiliary functions here, so I'll put it there. The other thing I need to do is declare it earlier up, so it knows it's happening, and we can see here there are some forward declarations, and we can just add print tree to those declarations, and don't forget to put a semicolon in. And we need to call print tree so we can see a tree printed, and we call it here in the main program. So we've got a parse tree here, we can just call print tree of the parse tree, and that's all we need to do. So let's see how that works. Let's go through flex. Go through Bison, go through GCC, run it through our test program. Lo and behold, it's printed something out which represents the tree, and if we study that carefully we might be able to see what the tree looks like. Or we could print out a lot more information to show how we can understand the tree, which it hints at in this file. This can be improved by translating some of the integers into their text values, but we can look at that in another video.